This is the first episode of the CERES podcast. And so we don't know how often we'll be doing these podcasts, but we thought it might be a good idea to try it out. And so the reasoning that we're looking at is a problem that we've been finding is our main priority at the series group is mostly on scientific research. And a lot of people are saying, oh, you should reach out into science communication. That's like a popular term to try and explain our results. But what we've been finding is that a lot of the topics that we're dealing with, they've become highly politicized. And so people, uh, science communication is kind of telling people these are the results, this is the science. But what we've been realizing is that actually we don't just want to let people know about what our results are. We want people to try and figure out themselves. So we think that there's something that's been missing is the idea of science education. And so we actually think that, like, just issuing a press release of our latest paper doesn't really tell a lot of people what's actually happening or how to interpret the science. So we're going to try and do with this podcast is to tell us a little bit about the about our work, and this is the, let's say, the format we were
Right, the format.
thinking of is that what we'll do is we'll divide the podcast into the first part of each episode. We'll review some of the latest science that we've been reading and give a flavor of some new research. And then the second part, we're going to look at a particular topic. And today we're going to be looking at this question that we often hear: do 97% of scientists agree on climate change? And we'll look into that in detail. And then in the final part, we're going to look at some of our own scientific research, our published work, and just look at a specific topic. And today, Michael is going to be talking about, well, three of us, but I think, Michael, you're going to be leading on describing our weather balloon research that we've done on
Yeah,
specifically
a
on
very small
polar
fraction
jets.
of it. Yeah, I think we're just going to confine ourselves to a new parameter that we have realized gives information about the balloon data, and that's molar density. And
Yes,
so
so we'll
we have,
discuss that. Yeah, and
Yes.
yeah,
Yes. So when we get, so that'll be in the final part. We're also anticipating that maybe in future episodes we might invite on one or more guests to talk about
yeah.
different
Some of our colleagues who's really are in depth and very capable of explaining many difficult subjects like the hydroclimatic variability. Dimitris Kosoyanis from University of
topics.
Athens and many
Oh,
more colleagues
yeah,
that are specialized in certain area where we think the topic would be very relevant to educate some of you. Indeed, we're educating ourselves. That's why the key part about science education is actually to, if you use the phrase properly, to kind of inoculate ourselves from all these media sensational headlines. And these are all most of the time is highly misleading. So and then it sort of dilute a lot of the key sign messages that I think that are important. I mean, we are facing a lot of problem in the sense that there is disinformation, misinformation, and all sort. Either aware or not, deliberate or not, but it's just the nature of our world that is a bit confusing. In some sense, this is why we're having a lot of this paralysis. That
yeah,
we're not really talking about science. Most of it are really public policy, energy policies, and a lot of this feeling. Like people's rough intuitions about what should be this and what should be that. So we
yeah,
hope that this kind of podcast would really get people more engaged and to seek direct source of data and be able to sort of share with their their churches, their families, even with their politicians and leaders of communities or schools and this and that, so that we can really have a very much more informed society and public communication in a sense. So thank you, Ronan, for
Yeah.
this
Okay. So
initiative.
let's get
Let's get
started.
started. Yeah.
Okay. So
That was a video that Ronan creatively make it really nice. I like it
uh,
very.
okay. So we'll. I think Willie, you shared a couple of interesting papers that are fairly recent. That
Yeah, this paper
identify.
is quite interesting because of all the Los Angeles fires and Maui fires and whatever, even the fires in Australia, and people started to blame it's global warming. It has to be rising carbon dioxide doing that, this and that. And
Yeah.
this
So
paper came out, I think, just 2 weeks ago, or even a week or so,
yeah,
in
this
Nature
is.
Communication, which is a prestigious publication, by the way.
Yeah. So this is Sean Parks and colleagues,
Yeah,
and
many of them like Park Williams,
yeah,
many of those guys are kind of well known in what you call the forest fire community.
yeah.
And
No, yeah.
go ahead. I think I put a
Yes.
context because this is actually a very beautiful paper in some sense because these people are collecting some like a database basically that's over almost 2,000 sites. It's called the
Yeah.
North American Tree Ring Fire Scar Network. And then they
Right.
look at the data basically historically. And how does that compare over time? So they can go back roughly 17th century, right? And then
Yeah.
compare to present time. In fact, one of the wordy statistics is that at 2000, so of all these nearly 2,000 station sites, they
Yeah.
actually found that basically at 2000 year 2000 there's only 6% of these sites have burned, have been burned.
Yeah.
But then if you compare with the peak year in 1748, roughly, in the 19th century, mid 19th century, oh no, not 19th, 18th century,
Yeah.
where actually they found that over 29% of the sites were burned. So that tells you, that's why the title fire deficit. But you can see the headline is trying to catch you that despite recent increase, this is actually a highly politicized issue, as you can imagine. So we just want to give you a hint how to read such a paper because it's politicized. Really, you want to get
Yeah.
published in Nature, you got to do this despite recent increase in area burn, because it has to be dangerous for society, so therefore give us more funding.
Yeah, yeah. Well, this is it. Well, I just to explain, they did this nice little cartoon schematic in the paper, which is their main result. So, what they're doing is you see this. They have like the arrow from there to there. The records that most people have been working on were from 1980s, 1984, I think, up to present, and they've been showing an increase in the total fire damage over that period. But what they realized is, if you actually, as Willie was saying, that tree ring network, looking at the scar damage all across North America, well, they weren't able to get some regions like the
It's a
tundra.
it's a very large region, cover North America, including of course our dear Canada, our friend. I
Yeah,
mean that cover. I think the statistic is over like 35,000 kilometers square. Yeah, some big area. Yeah,
and what they do is that they notice that actually up until the 18 mid
80,
19th
let's say. Yeah,
century, late 19th century,
right.
the it was much greater fire every year, much more greater fire every year. But they were doing a different policies because at the time, and this is like this goes back to it. I'd be curious to know what it was like before Columbus arrived.
Right, right. The natural role of fire. Wildfire has a role actually ecologically,
Yeah,
environmentally, so on and so forth, right? Because it's how seed got spread and this and that. So
yeah,
anyway, Rona, let's not delve too long into this, right? Because we got
yeah.
two more
But
papers. So
just to show you what they're saying is that
right,
there was actually much greater annual fire, and then there was changes in practices with modern society
right.
shifted to actively suppressing fire
Fire.
instead of allowing it to naturally go, or even starting it. And so that reduced the fire, and now it's increased. So, but there's, compared to previous centuries, there's actually less fires each year.
Right.
And then this was an
Maybe
interesting.
the answer is that, excuse me, it's more about fire load. The trees
Yeah,
there are a
fire.
lot more loading. Back then it was less urbanization, like we don't chop down all the trees. I mean, yeah, the pilgrims when they come, chop down trees
Yeah.
of Virginia, things like that. But anyway,
So interestingly, this journal allows has a nice feature where they actually publish the peer review comments, which are usually anonymous and not available to the public.
right.
And so a couple of people caught this interesting comment here in the
Yeah, yeah.
peer review, that the one of the reviewer too, one of their opening criticisms was, I see this paper as potentially being used
Used
by
by deniers
deniers
of
of
climate
climate
change. Right.
change impact. Consider, if possible, some rephrasing here to put even more emphasis on impact rather than on burned area. And then the authors, to get it published, and
Heavily
maybe they
complied
believe this,
also.
but they said, we share the concern that climate change deniers may misuse our findings. In
Yes.
fact, we spend a large portion. So that's just an interesting point, just to
Yeah,
say.
for normal people, you may not understand, well, how does a paper get published? There's a lot of this kind of hanky-panky involved, which actually we kind of find it a bit distasteful because it's not so. Well, science is done by human beings, so that's all the conclusion is. I think. Let's move on, Rona. Come on.
Yeah, yeah. Okay, well, here's the next one. This one is by Professor Ross McKitrick.
Yes.
It was just
It,
published.
it's a hot topic because the history of this is that it's called social cost of carbon. I mean, people may know the history. In April 2nd of 2007, the US Supreme Court has to decide. It was a state of Massachusetts, actually a bunch of states suing the EPA to try to say whether we should regulate carbon dioxide. Remember, CO2 is a gas of life. It is a biological truism. It's a fact that you cannot change. But a lot of these activists trying to insist, just like the way that they claim CO2 causes global warming, but they try to insist that the beneficial impact in biological sense and environmental sense and ecological sense should be overwhelmed by this global warming impact. So they actually challenge. So Supreme Court make a decision 5-4 for this, basically label CO2, atmospheric air CO2, as an air pollutant so that US EPA should regulate. So, and then in 2009, immediately the EPA, which is run by the Obama administration at that time, insist then they put out a thing called CO2 endangerment findings. And then that's where they try to say that, the social cost of carbon is extremely high. There's all negative, no positive. So, Ronan, can you just explain the
Yeah,
paper?
well,
I'm most
well,
familiar with this
so
paper.
this is just as you can see in the abstract. I don't know if your people are listening; they might not. If you're watching the screen, we're sharing these slides of this, but they had so it was specifically in the Biden administration went and updated the social cost of carbon being carbon dioxide emissions, and they did that based on a study. There
Done in
was
2014, original, yeah.
Yeah, well, there was a paper in 2017 that calculated
Right.
the social cost of carbon for agriculture using a study by Challoner et al. 2014,
Mm-hmm.
and that had contained nearly 2,000 uh, studies itself. It was
Records,
a
yeah.
big meta-analysis,
Yeah,
but
it's about relationship between temperature, atmospheric carbon dioxide, and crop yield. Like corn,
yes,
wheat, and so on and so forth. And
yeah.
yeah, you can see what Ross McKitrick really, really a brilliant what you call economist and climate kind of scientist. Ross McKitrick is very good, even in terms of data analysis and climate science. Actually, very knowledgeable. So he went and looked at this suspicious study, by the way.
Well,
So,
well,
Ronan,
they found is that the study he realized that he could update a lot of the studies from that original one.
data
That there
sets.
was actually information available that the authors hadn't used. So when he did that, he was able to
Yeah,
increase.
he added 40% more data to the database. I mean, it was 860 increased by 1200, right? So
Yeah,
it's 40% increase, and shows that the conclusion changed completely. That's what is so interesting. It shows
yeah.
you that
So
you don't pick a selective data set, okay, and
yeah.
then trying to say that, oh, here's our conclusion, but it's just non-robust in statistical sense. And being a statistician, I think Ross McKitrick is rather serious. Again, we're not trying to promote that you should run science by narrative, doctrine, and so on and so forth. You just have to base on real data and complete sets of
What
data,
an
good
important
data set.
the important point here for people that are following along and trying to figure out, or what do I do? What this study has done is that it's shown that the science can change, the conclusions can change when the data is updated, and it can change quite dramatically. So this is an interesting thing. So this study, Moore et al. 2017, had gone and used this Challenger data set,
Mhm.
um, and they had concluded that the crop yields are going to reduce dramatically with any amount of global warming. And then that then was added into the US EPA's estimate of how expensive carbon emissions are, and that's then going to influence government policies. And a lot of
By
cases,
the way, all of us will be extremely rich if we follow their logic. Social cost of carbon, because oh, here's $10,000, buddy. I mean, this is how that kind of really bad movement to try to, just because they want to regulate, they have to invent this kind of artificial thing called social cost of
Just to summarize what Ross found was two things. One,
carbon. Right.
that by using a more complete data set, he got different trends than
Yeah,
the.
Roland, show the graph here.
But
yeah,
the other thing that was left out was that by increasing the level of carbon dioxide in the atmosphere, it acts as a fertilizer, which increases the crop yield.
yeah.
So in greenhouses, for example, they artificially increase the amount of greenhouse or carbon dioxide in the greenhouse so that they can increase their
Right, I
production.
will put it this way: Raw's conclusion is less surprising than the startling conclusion by this other previous researcher who are rather not careful or have some other opinion in mind. That is very strange. Actually, this is why it's completely taken up by the all these politicians and trying to force
I,
EPA to make it that, oh, is increasing
yeah,
carbon
well,
dioxide going to cost money.
Yeah,
I
just to
think just
show explain this kind of, because I don't
Yeah,
like showing big graphs, but this is the amount of warming, and this is the average of all of the studies in the old one that the US EPA effectively used, the blue.
the blue. Yeah,
And this is the change in crop yield for maize, millet, and sorghum. This is for
rice,
rice. This is for
wheat.
soybean. This is wheat. And you can see for all of these crops, even a little bit of global warming in degrees Celsius, you get a reduction in crop yield for wheat, for soybean, for rice. Although interesting, it tips up there at the end. They don't explain that. And
Right.
then the maize, millet, and sorghum, which is huge things. Now, McKitrick's update adding in more information
40% more data.
reverses that, so
Yeah.
that actually you will expect an increase in yield with modest warming and even substantial warming, up to 5 degrees for all four of these crops. Now, the in McKitrick's paper it explicitly says at the end that he's just looking at the effects on crop yields. And so beyond the scope to look at the impacts of global warming more generally. But he points out that the current US EPA social cost of carbon is heavily weighted. It's mostly due to this to these blue results, and that's gone now. So
Well,
Uh,
that just give you a thing. Don't US EPA should be updating their CO2
yeah,
engagement
well,
finding?
maybe
That is a
the
controversy now, but I hope they get to do it because this is how science should inform policy rather than policy changing science. I mean,
yeah.
it's a very good perspective. I think Ronan, let's move on.
Next,
Yeah, the
next one,
whole
the
point is
last
that
one.
not no none of the green thing is below negative science. You know what I mean? Yeah.
So we just got to briefly just we have been doing a lot of research on COVID-19. Unfortunately, we're because we're on putting this up on YouTube. YouTube's community guidelines is very very strict when it comes to talking about COVID-19 and in particular about the vaccines and treatments. And so. Uh, if you are to talk about it, you cannot discuss science that might disagree with the World Health Organization's current positions, which change over time. So, but you're not allowed to. So maybe at some later episode we might do a podcast on
Yeah, yeah,
Rumble
Ronan, let's
or
move on. I mean, yeah,
where you can
disclaimer is
actually
one thing.
talk where we can actually talk about what the science is actually saying.
Right, right.
But while we're on YouTube, we can only talk about science that agrees with the WHO statements, and that is that the COVID-19 vaccines are safe and effective. But we can briefly talk about this new preprint because they say that more serious or long-lasting side effects of COVID-19 vaccines are possible but extremely rare. So if we were talking on Rumble, we might have a different conversation.
Yeah,
But
the key
here,
word is like what is extremely rare, and it's
yeah,
always a
yeah, yes.
fake science using word to replace the people notion. It's just completely a goobly doo. Anyway,
Yeah.
so let's
So,
move on and talk about this
but
paper.
this one
Sorry
here,
for not having too much patience for this.
yeah, yeah. So this is a preprint that's published by Yale, and they don't contradict that because they don't quantify how rare or otherwise this is. But what they have done is now it is a preprint. Hopefully, this will be accepted. But because it's got a lot of prestigious scholars involved, they've been working with patients with dealing with long COVID, and they've been noticing that a lot of their patients have very, very similar uh, symptoms to long COVID, but that they actually develop those symptoms following
After they got the vaccine,
vaccination as opposed to the actually contracting COVID. And so they're saying this is they're calling this the post vaccination syndrome or post acute COVID 19
yeah,
vaccination
PVS or
syndrome.
PACVS. Yeah.
Yeah, and they say, unlike long COVID, PVS is not officially recognized by health authorities, which has significantly limited patient care and support. And this is a big problem.
Right.
So they, at the moment, these patients that are suffering from a vaccine-induced, uh, some people call it long-vax, but it's post-COVID vaccination syndrome. They only way they can get treatment is if they pretend that it's associated with COVID. Um,
Okay, Ronan,
and
time.
yeah, and so there it's an interesting study. It's preprint, but they did point out, yeah, people were coming down within 1 day of the vaccination. So this was clearly linked to the vaccine, not to COVID. They're also finding that
Yeah,
elevated levels
measuring
of
the
spike
spike level.
protein in circulation up to nearly 2 years after the vaccination, which is quite disturbing. So, with this, and we're not commenting on how rare or not it is, but we would recommend anybody that is interested in this, you might be or might have symptoms like this. You might be interested in following Pierre Corey. He has a Substack, and as he pointed out here, that he's commenting on this paper preprint saying that it's a disease that before this paper did not exist, despite the fact I've specialized in diagnosing and treating it for over 3 years. So, he's been a bit tongue in cheek there, but it's
Yeah,
like this is a problem. So hopefully, people who are suffering from this, and YouTube, we're not commenting on how many that is.
Right,
Uh,
right, right. You too. We
but
apologize in advance. Just don't
yeah,
block
yeah, yeah. But okay, so I think now if we kind of we can I guess
Yeah,
yeah
let's
we
go to
got
the
to
next one, Ronan. Yeah, it's
yeah,
already
yeah. So
25
now
minutes
that's
into it.
part two. We got to talk about this claim that you'll often hear, and we are continually being asked about this. 97% of scientists agree on climate change. So generally, what people will do is they will say, when they find out that our work disagrees from some of the things that they have been taught, they say, well,
Well,
97% of scientists disagree with you. So,
yes, I have been personally challenged by Al Gore once. I mean, that do you mean that you disagree with 2,000 scientists from the IPCC? I say,
yeah,
yes, sir. Should I educate you on what science is about,
yeah,
Vice President Gore?
yeah.
Anyway, it's a tongue in cheek, but it's just terrible to try to treat science by voting. It's just by narrative, by all this. It's ridiculous. But anyway,
yeah,
this is the world we live in. Ronan
yeah,
now can explain this sort of. By the way, we don't speak on this issue without actually very thorough investigation. I want to give credit to Michael and Roland because this topic has been what you call, people thought that, oh, we understand everything. But
yeah,
every time Ronan and Michael study this issue, they will come up with something unique insight because they read everything. And then I think that's a result of this, why we are confident in speaking about this, and we felt we have something great to offer. So we
yeah,
hope that you will pay attention to this a bit. Plus, that if you
yeah.
have any question, please reach out to us. We're always ready to answer good questions. So please.
So if we look at this is just the timeline of. So I think most people that are watching this would have heard that 97% of scientists agree, or 90% or 95%, all of these things. I just, and this is, where did that come from? And actually, when you look at it, in the beginning, in the 90s, you would hear it, as Willie was saying there, they'd say
I'll go.
the overwhelming scientific consensus. But these were just assertions, like made by NGOs, non-governmental organizations like Greenpeace, and then uh, the activists like our politicians like Al Gore, and there was no. It was just an assertion people were making. The first attempt, it seems, to actually claim that it was
It
a
was a
consensus
quote unquote
was,
scientific work, yeah.
yeah, well, I call it pseudoscientific, but anyway,
Rona,
scientific.
Michael has a great saying, right? We are fighting campaign versus science. I mean, that's a problem
Yeah,
because we have a
yeah,
huge disadvantage. By the way, this is why our mind really like this kind of headlines and all this nonsense and firm conclusion. They don't want to hear any issue-washy or the details. But Rona now will give a bit of details. Yeah, it started with Oreskes, Naomi Oreskes, who was at
yeah,
UCSD, and
yeah,
then now is at
yeah.
Harvard.
Yeah, so Oreskes 2004 was just a one-page article. She went and she looked at abstracts that had the keywords global climate change. And then she looked through the abstract. The abstract is that short summary
Of a
of a
scientific
scientific
paper.
paper. It's like you saw a few we were looking at in part one. We were looking at some
That's
abstracts,
right.
just that 250 word summary of what the paper is. And she skimmed through, or maybe read through 928 and said, "Oh, none of them disagree with the consensus." If that was her opinion, and so
Yes, Al
therefore
Gore
she
in her
said,
book, in his book, An Inconvenient Truth, have that number 98 versus 0. I mean,
"Yeah."
round of applause.
So that the actual surveys, so that's just readings, abstracts of papers. The actual surveys of the scientists asking them what they do was Doran Zimmerman in 2009. Now, they surveyed, this was Maggie Zimmerman, was a master's student working for, is it
Oh,
Peter
Peter
Doran?
Doran, University of Illinois. Yeah, yeah.
Yeah, yeah. And they surveyed, they got results from 3,000, more than 3,000 Earth scientists. And the initial results, actually only like 80 something percent, we'll talk about that in a minute, actually agreed with what they thought. But they then went and got a subset of 79 of those 3,000. And they said, well, 77 out of the seven, or I think
Right.
it was
7 out of
76.
79 is 97. Yeah.
Yeah, 97%. And that was it. And then that went viral. And people started repeating that. Then in 2013, there was another one, which is not surveying scientists, but again, doing what Oreskes is, just surveying the abstracts. And they said they went and they claimed only 3% of the papers expressing a position disagreed with the consensus. So then they say 97% of papers agree. Then Barack Obama misquoted that.
By the way,
But
in real time, is the sitting president of the United States was
I,
tweeting this out, so therefore they get a lot of eyeballs. I mean,
yeah.
but the paper is completely flawed. Yeah, we'll explain.
And then more recently, you have Lynas et al.
Hardliners, yeah, yeah.
They claim to have done an update
They
of
have
Coconut.
increased. It's 99%.
Yeah,
Exceed.
I think they're even saying could be 99.7% or something. Let we get onto that. But Michael, this was
Michael led this study. Yeah,
yeah,
beautiful.
this was a report that we can get. You can find it on ResearchGate, and I think we can put a link in the description for this report that we did on Greenpeace, which one of our co-authors on this was Dr. Patrick Moore, who is one of the co-founders of Greenpeace.
Greenpeace
And
itself.
He was, in fact, the only scientist in the group.
that started of the founders.
That's true. Yeah, yeah.
And it's a well worth reading the full report. But for this particular discussion, in section 4, we have a discussion on the use of 95%. So, Michael,
96,
did you want
97,
to
98. Yeah.
wait? What is the significance of that number of 97% of 95%?
Power of
Well,
advertisement. Yeah.
it's you can never say something is 100% because if somebody then finds a flaw or finds some that isn't, then your argument falls. But if you say 95% or something like that, then someone comes along and says, well, somebody disagrees with that. Then they can say, yeah, but there are 5%. But when you're coming to marketing something, or if you're trying to push an agenda,
Yeah.
you try to, they will come up with something like 95% or 96% or
By the
92.
way, Michael, can you explain that this is actually well stated also in so-called the handbook of all these NGOs, especially Greenpeace people, right? What's the book
Yes,
by the guy Rose?
yes.
Yeah, well, Chris Rose gave some things. I'm not sure does he specifically mention. I think he gives. Yeah, I think the idea is if it's more than 90%, when people will automatically in their head say pretty much everybody, and they found that even back in the 70s and 80s when they would be marketing like cat food. 9 out of 10 cats prefer this,
Right,
or
right, right.
9 out of 10 dentists
For
recommend
the
this
dental
toothpaste.
toothpaste, yeah,
Yeah,
we all
yeah,
like Crest. Everybody use Crest.
yeah. And so if you say 9 out of 10, then people say,
Very acceptable number.
yeah.
Anyway, let's move on. Let's move
It,
And,
on.
and
it, it is a
what they
marketing tactic.
realized, yeah, it's a marketing tool, and people realized if you just say it, that a lot of the times you can get away with it, and it just get if people do it. So most of the 97%. So the idea, the people that are doing this, they wanted to find the figure 97%, or 95, or 96, or 98 has to be greater than 90, less than 100%. And so the first two, again, like you said, science. I do think pseudoscience is suitable for like Oreskes, or the claim of 97% because it is. It has a high-profile paper journal,
Yeah, in Science
just
magazine.
one page, And the same with the Doran Zimmerman. And, like, actually, if you read Maggie Zimmerman's thesis, is quite detailed. And she actually apparently, after decided to leave the whole field because she started off thinking, oh, yeah, all scientists agree. And then when she got all the surveys in, she started to realize actually a lot of scientists don't agree. But essentially,
Okay,
what they did is,
let's go to the details. Yeah,
yeah, they asked two questions. They said,
it's hard
the
for people
key
to
one
read,
is,
so just read it out quick.
yeah. They said, when compared with pre-1800s levels, do you think that mean global temperatures have generally risen, fallen, or remained relatively constant? So that a lot of people, if you're not familiar, that was a period known as the Little Ice Age. So is it warmer than the Little Ice Age, is what they're saying. And then, do you think human activity is a significant contributing factor in changing mean global temperatures? Now, a lot of the public, when you hear the word significant, significant has a different meaning to scientists than to most of the world. Most of the world, when they hear significant, that means you think substantial. But in science, it has a specific meaning because you can say something is statistically significant, for instance, if it's more than 5% chance. So, so people will when a scientist says significant, that means non-zero, or not negligible. So when you ask a scientist, do you think human
You
activity?
have different levels of significance too.
Yeah,
You can say it's significant at the 1% level, or it's
yeah,
significant at the 5% level,
Yeah,
or
Ronan,
I,
again, science cannot work by consensus. Let's move on a little
yeah,
bit.
yeah. So if you were just saying, so most scientists, a significant just means edited, maybe 5% would be significant,
Right,
whereas
right.
most people, you're thinking the majority. Um, Only 80%, or less than 80% of the respondents actually said yes, they think it's significant. Also, they didn't say what type of human activity. They didn't ask, was it CO2 or greenhouse gases, urban heat islands, anything like that. But what they did is they then divided and they found a little subset of 79, actually 77, and they said
Yes,
75 of these 77 said yes.
yeah.
That's
Less than
not.
97%. Yeah.
Yeah, so we there have been other studies since then, and what we've realized is we've compiled together some of the main ones. And here's the thing: actual surveys of the scientists. What do scientists say? So 90 to 97% of scientists agree that there's been climate change, that the climate has changed, and that
There
there's
has
been
been
global
global warming.
warming. I
so do we.
agree. What?
Yeah, I agree.
Yeah, yeah. Now, the majority of scientists, but not all of them, it's not 97%, like maybe 70% or more, believe human activity is responsible for at least some of that. So
Again,
that's a
at least some
majority.
of that 1%, 2%, 10%, I don't know, 90%.
Yeah.
Yeah.
But if you want to just say that and go to weaker and say 70% of scientists agree, yeah, or even
But you
78.
also should be saying, but 30% don't.
Yeah, 20 to 30. It depends on the
But
survey.
then look at the next bullet point.
Yeah, but if we were to do the same thing, you could say, well, actually, 60% or the majority of scientists also believe at least some is natural.
Yeah.
So, and then here, this is really it. So we've colored from red is entirely human caused to gray is don't know, blue, dark blue is entirely natural. So you can see it's true that there's more that think it's entirely human caused than think it's entirely natural. But actually, most scientists think it's a mixture of both. And they debate, they're not sure on exactly how much. So
So this
with
is a
that's
great
what
slide that Ronan has pulled out from these statistics, all these surveys,
yeah.
and
So next time
show
you
that you can
hear
go either way. All this polling stuff is a bit, yeah.
Yeah, so next time you hear somebody saying 97% of scientists or 90% of
Bring up
scientists
this graph.
What,
agree,
what,
on
What you should
climate
say
change.
is this is some sort of advertising statement.
Yeah, well, you can't
When
say
I
that. Yeah,
really
yeah,
like
Yes,
yeah.
you can, Ronan. Come on, you should be able to say that freely.
Yeah,
You
you
can
can say
say
that.
that.
Or the other way, what I was trying to say is next time somebody says 97% of scientists agree on climate change, you can say, yes, they agree that there has been climate change.
Right.
And then they say, oh,
But
but
it doesn't
humans
tell us anything.
causing. No, no. Then look at these. And by the way, these are surveys of the public. And actually, it's not too different because the majority of the public agree the climate is changes. A majority of the public believe human activity is responsible for at least some, and the majority believe at least some is natural. Um, so they're not that different. The public kind of is agreeing. So again,
Oh, there
it's
you
hard
go. We got
to.
a consensus there.
But let's just talk about this.
Yeah, yeah. This one is very, very big. We got to talk
Yeah,
about this.
so this is if you're not doing so. This is Barack Obama was president of the U.S. at the time,
At
and
that
he
time.
tweets out this study, which is kind of unusual for a president to be tweeting out a scientific study. So it got a lot of attention, and they said this is Cook et al. They said they examined 11,944
Abstract.
climate abstracts from 1991 to 2021, and they found among abstracts expressing a position on anthropogenic global warming or AGW,
That's a keyword. Expressing a position on.
yeah, 97.1% endorsed the consensus position that humans are causing global warming. Now, notice this is not what Barack Obama, he said 97% of scientists agree climate change is
Yep.
real, man-made and dangerous. Now that's, and he's linking to this study, that's misinformation or disinformation. It's
Yes, we
not
can
clear.
accuse the president of the United States for doing that. Indeed.
Well, maybe he didn't read it, but
Because
he tweeted
they
out on
really
his
don't care much
platform.
about science. I mean,
But
science is just
the
a convenient,
bottom
convenient
line is
title.
that it's climate abstracts. It wasn't a survey of scientists. And then it just says that humans are causing global warming, some global warming. It doesn't say that it's all. And then they didn't say that it was dangerous.
Yeah, it's
Okay.
also not about scientists. It's not number
Yeah.
of scientists. It's number of abstract.
Now, you,
Sorry.
Willie, you did a paper with David
Yes, the
Legates
great
and
David Legates of University of Delaware and Christopher Monkton and William Ambrix. Yeah.
okay, and so you
When
went
we
to
saw this, I mean, we just say this is such a puzzling nonsense. Then we should actually dig deep, go really deep into the details. The first thing you realize is that out of the almost 12,000, almost 8,000 of them express no position. And then you can see there is only 3,000 implied position. That's 25% on your left if you look at the graph. And then only 1,000 of them explicitly have some claim or and rather. So that's 8%. Now let's zoom in the 8%, the 987 abstract. You will see that it's a, oops. Now we got a little technical problem. Anyway, the bottom line, let's hope Ronan can get back. But the bottom line is that when we look at the details of the even the 64 papers that they claim to have an opinion, that claim to have a consensus on this human caused global warming, we actually don't even believe in the 64 because we checked all 64 abstract and we found that only 41 of the papers says that believe have this consensus global warming. If you take 64 divided by 12,000, that's 0.5% actually. That's a proper way to view this, not 97%. And then if you take 41 over 12,000, that's 0.3%. So I think you can really, really debunk this very cleanly because this is just numerology. That 97% is actually a very specific nonsense that they created. So, Mr. Cook, I apologize. You are such a great politician, and congratulations. And of course, you belongs to the class of President Obama. Unfortunately, I'm sorry. Politicians should never impose their worldview on science. Science is such a precious topic that it should be untouchable. So Ronan is back now. So
yeah, yeah.
I think Ronan, I kind of go through my words. You just maybe put back the slide. That should work. I think
Yeah,
it's sufficient
yeah,
for us
yeah.
to
Okay, so
discuss
we
the
can we
topic.
can go. So shall I move on to now? Let's move
I
on.
believe we should move on. Yes.
So this one here, we're looking at the Lynas et al. Study. They claimed they got even more. They actually claim more than 99%
By the way,
of
Mark Lynas is also a well-known activist who threw a pie on Beyond Lombok. If some of you may care to know,
well,
he did this
I
paper
will.
because he got a fellowship at the Cornell University, so he tried to.
I will say that, like, in terms of that incident, yeah, that so I think that was around 2006 or seven,
Right.
that he went to a book signing or something of Bjorn Lomborg, who was quite kind of skeptical of some of the claims. But Mark Linus has later apologized and actually said that he was wrong, and that he agrees with Bjorn Lomborg on nuclear power, but he still is pushing this thing about the consensus. So he did
Consensus. Yeah.
this claim quite recently. What they did is they went and they identified 88,000 papers, and this is from
First of all, you
2012.
notice that it's published in the same journal, Environmental
Yeah,
Research Letter. So you know this journal is well known to be to be the
yeah.
kind who would really happy to receive any. If you have any, like the one that we our analysis can be publishable. If you want to go to this journal, you bet that you will be rejected.
Yeah. Okay.
That's the way it works this day.
Yeah.
Oh,
So
very sad.
they did two parts. One is they randomly picked because they didn't have time to read through all 88,000 papers. That's okay, fine. They took a random subset of 3,000. They read through the 3,000, but they claimed only four were skeptical of the IPCC position that global warming is mostly human caused. Then what they did is they used machine learning to rank all 88,000 based on how likely they were to be skeptical. And then they took the top 1,000 most likely to be skeptical. And then they looked through them and they said only 28 of them were actually skeptical. And one of those had already been mentioned. So that means in total that there's only 31 papers, according to them, were skeptical out of 88,000. Now they admitted maybe they missed a few, but they were saying they got most of it. So how did their analysis work out? Were they representative? Because that's quite, if that result is valid, if that analysis is true, well, yeah, 0.035% out of 88,000 papers is a very small amount. Well,
Notice that these
interestingly,
are partly the standard trick, okay? That the way they do this, that they were so careful, it's only few percent. We may have missed a few. That's a bit of a very standard kind of campaign, and to make themselves even far more convincing that they should be.
well,
But I think most people know that. But let's
yeah,
discuss.
in fairness to like Lynas et al., they did a good thing where they actually provided in the supplementary material all 88,000 papers. So we looked through that, and we actually found a lot more papers just in about an hour. We went through, and because we were familiar with the literature, and we were able to identify dozens of papers that were, just quickly, just looking for people or colleagues of ours that had written papers. But I think you can speak because four of these papers were you were co-authored,
Yes,
and so none of these four were in that random sample of 3,000.
I'm
But
curious if Mark Linus may be aware of that. We'll just.
yeah. But
I
they
hope Mark
were
Linus watched this. Thank you.
yeah. So paper one, these are the four papers. So paper one was included, so their machine learning
I can
algorithm did
assure you that this is
identify.
already far more selective than that, because believe me, we have published more than four papers during the period that they survey. It's just telling you that the sample was all highly selective.
Yeah, well, it was a sample they used. I think they used the criteria. I think they did something like global.
Yeah, yeah,
They
yeah,
used, they got 88,000. There's millions of papers out
yeah.
there
Yeah, out
if
of
you
it, indeed.
wanted it. But like they said that this was possibly, but they went and they said no, that this paper offered no position, and so therefore Willie and his colleagues
It-
are part of the consensus.
But it's
So is
completely
that
untrue. The point of that paper, actually, this is a very beautiful paper. It's a paleo study of giant clams, right? You study the chemical, you measure strontium calcium ratio, then it's a sensitive to actually sea surface temperature. What we show is that for the past 2,500 years, the current warm period, it's just it's a bit much lower than actually medieval warm period and even the Roman warm period, which is really was basically the paper. How could you say that we believe in the consensus based on this paper? It's just,
yeah.
sorry, not plausible. This is why reading an abstract and misrepresenting like this is rather not healthy. It's just not the right
Yeah,
thing.
it's
I'm
not
sorry
a
to
good.
remind
That's
that.
not how you do science. And
Yeah, yeah, yeah. But
I should mention that, like, yeah, the abstract, you really can't comment on is if you want to if your paper is skeptical of the IPCC or the consensus, you you really you want to avoid being too explicit about it in the abstract because you'll find it harder to get published. But you can describe your results in the conclusions and the things you try to avoid
yeah,
being
we
too
speak about
confrontational.
another even much more dark issues about self-censorship in that sense, because some of us skeptical scientists, it just sometimes it's just very, very hard because every time we send a paper, it took 2 to 3 years to get published. Those guys send it less than a week.
Yeah,
They have no peer review. They have power review system, which is
yeah,
what points to another thing that I'm sure it come up in our podcast over and over again. A lot of these issues about scientific publication is a bit unhealthy now. And let's see if we can fix it by making people more aware of it, because most of the money come from public funding. So people should be much more educated on that rather than being sitting passively to say that,
yeah.
oh, our taxpayer money should go to fund this sort of thing, this and that, where
Oh,
who decide,
yeah.
and we're
So
not doing science. Embarrassing.
just to kind of wrap up this
Yes.
study, the other three papers didn't get their machine learning didn't pick them up as being in the top 1,000 likely to be skeptical. So is that correct? Did their machine learning algorithm were those not skeptical of the consensus?
Hell no. But yeah, especially paper number 4, Mountain and all that paper was featured in the journal, the top science journal in China actually. And
Yeah.
once we got in, by the way, we're no longer able to publish in that journal because that paper created it was make the front page of the journal. Actually, I never had a paper being selected
Uh,
as the main paper, but it was a
but
good paper. It was explaining why the model run hot, the
yeah,
ratio, of prediction versus the thing fail. I mean, but of course that you couldn't say that it didn't count as something skeptical about
yeah.
anthropology.
You those two papers
It
in the
clearly
follow up.
is. I mean, I'm sorry. Yeah.
Yeah, yeah. They actually went and they said no, that it's much less warmer than the models are saying. But this one is quite ironic that the Legate sort of Briggs,
Yes.
that was a prequel to the one that Willie you were talking
That
about
is the
earlier.
paper in a sense that what you call criticizing the Cook et al. 2013 paper, if you all
Yeah,
may recall.
you were specifically saying the perils of
Errors of consensus
consensus
knowledge.
knowledge. You were explicitly criticizing the use of claiming scientific consensus.
All right.
Anyway, that's Lynas et al. 2021.
I think
And
let's wrap it up.
we just to wrap up, and then it's like this is. I think it's just to say you've seen. So now, hopefully, people that are watching it now know what how the sausage of 97%
Was
consensus
really was
was
made.
made, and I that it isn't true. But just to wrap up, the bottom line is, as Bert Rutan pointed out, science is not about consensus, and consensus is not science.
Yeah.
Uh, if you were doing, if all of the scientists agreed on a topic, then they stop it. It's all done. You don't need to move on. It's science thrives when people disagree with each other. Scientists are always disagreeing with each other. That's how science progresses because you say, I disagree with you, I got to prove, I got to test it. So as soon as you're getting claiming that all the scientists, or most of them, are agreeing, then you know that you're not doing science. Now you're into politics.
Yeah.
And I
Yeah, and
think,
by the way, another very great essay which Ronan quoted here is this lecture, excellent lecture by the late Michael Crichton, right? I mean, Michael
yeah,
Crichton is a great man, I have to say. This is a great man who actually believes in science. He's not trying to take side. He just simply say, can science speak itself? I mean, this is why I think to add flavor to that, we are also some. I mean, I myself can take a minor credit because it was my colleague Sally Balunas, because she knows Michael Crichton directly. We were able to persuade Michael Crichton, after his essay appeared, to come and actually testify in the U.S. Senate, the Environmental Public Work Committee, and he did it once. Everybody should look at the video. Such a powerful delivery. And people keep asking him to do it. He said, "No, I'm not doing it again. It's enough." You know, science turning into religion is a very dangerous thing.
for anybody who is not familiar with Michael Crichton, you're probably very familiar with a lot of his work.
Yeah,
He was an MD, and like very intelligent man, but he's also a writer, a
yeah.
director, a
MD, PhD from Harvard Medical School, postdoc at the White House, White something institute at Cambridge, one of those medical
yeah.
institutions.
He wrote. If you watched in the 90s, there was a very popular TV series called ER, about like a medical drama.
Oh
He
yeah,
also wrote Jurassic Park. He wrote a number of books. So if you've watched any of the Jurassic Park
Andromeda
films,
strain,
that's
and all of
Michael
that. Yeah. By
Crichton.
the way, all this virus stuff.
Oh yeah, he also did that, and then in towards the end of his life, which he died prematurely of like it was a heart
Cancer. Yeah, it
attack
was the
or
cancer.
cancer. Okay, anyway, he said in this 2003 that consensus is invoked only in situations where the science is not solid enough. Nobody says that the consensus of scientists agrees that E equals mc squared. Nobody says the consensus is that the sun is 93 million miles away. It never occurred to anyone to speak that way. That's the point. You don't. Science, if there's facts, if everybody is an undisputed fact, you don't need a scientific consensus on it. You just present it. And if anybody disputes it, they can go and try and do it. So, yeah, so that's consensus.
All
Next
right,
time
let's move
anybody
on to part
says
three. Ronan, is an hour
yes,
into the thing. Yeah.
yeah. So let's go on to the last bit.
Yeah, now here's the goodie. Here's the baby
Yeah,
of Michael Connolly, the great man.
yeah. So
It's a
um,
privilege, Michael, to work with
yeah.
you.
Now, Michael, we're running a little bit longer because this is we're still
It's
learning.
okay, it's okay. But
But
let's.
so it's over to you. We want to talk a bit about it, but I'll just introduce some of the basic topics on what we've done and this idea of molar density, and just to say the type of work that we've done. So, uh, Michael and I, for those that aren't familiar, before we started collaborating with Willie, we spent like years on a researching from like 2010 to 2014. We started looking into into climate change because we started to see some scientific problems, and so we found that there's a lot of different papers, or we decided we could write these up as scientific papers, but they were all quite long, and we saw that they were undermining key paradigms. And we said this is not it's not going to get published in a standard peer reviewed journal. And we said let's just set up a new open peer review journal and put up all of our analysis, these working papers, and let everyone look at it and let the public view it rather than waiting for
Uh, A, a lot of people, when we set up the open peer reviewed journals, which allowed anybody to come in and make comments on our work, they
yeah,
said that it would be inundated with rubbish. But it
yeah,
turned out that wasn't the case at all.
yeah.
Uh, we found we had very interesting debates with people going on.
Well, it's a new paradigm for science. I mean, I wouldn't even call it new. In fact, in the past, it's always open. I mean, there was a lot of secrecy
But,
now in peer review that becoming
but
a bit of a problem. But
What we
anyway,
did,
let's move on and talk about the main.
I just to give the background
Sorry
because
that I'm rushing because of
yeah,
the time constraint.
yeah, no, but we'll give a bit of the background and to explain these papers. We would recommend that you read them. Anybody that's interested in them, they're more detailed. You can still
well,
find
I
them.
think, Ronan, just what we should point out here is these papers that we put in this open peer reviewed journal didn't go through the standard peer review process.
Yes,
Uh, so we call them working papers
yes,
uh, for that. But since then, we've had 20, 30 peer-reviewed papers going through the standard peer review process. So
yes,
what we're going to be discussing in a few minutes are actual papers that have gone through the standard peer review
By the
process.
yes,
way,
and
I
it's
just speak from my own point of view. As again, you
yeah.
guys might see already, three of us always disagree on things. I can tell you, as an independent scientist that practiced this science for a long time, this paper is groundbreaking. Each of every one of them is crazy good. I mean, it is. It really does put us down a little bit, calm down about how much we don't know. And Ronan and Michael are truly unique individual scientists that is couldn't care less about how the world thinks, and then they really think very quietly about all this topic, examine in thorough detail. This is why each of the paper is really thick. I mean, I apologize in advance again, but it's beautiful work, and please read them when you have a chance. But hopefully, we will inspire you to read some of this stuff. But we are continue to try to get it out there in the public sphere in a peer review sense, so that we can publish it in a standard way like normal people. But even this is more than sufficient. I would say that when I try to review some of this paper, I mean, it's clearly well done, well done in terms of every aspect of it, the analysis, the context, the review of the subject. Each of them are highly knowledgeable and add actually not add a bit of knowledge for this particular work on a balloon is truly unique. I think it had a change of paradigm potential. So let's move on, Ronan. It's beautiful
Thank,
piece of
thank
beautiful
you for
work.
those kind words, and then we'll go down. So I'm just going to.
Ronan didn't pay me. Just kidding.
Yes. I'll just describe one of the bits. We just got to focus on one aspect, but you can read the papers for other ones.
Yeah, and many other
This one
papers
we're
of different
looking at
subjects.
weather balloons. So the just a bit of terminology because you'll see this. The there you'll hear people saying radio sondes, and what they mean is a weather balloon. So a sonde comes from the French for a sounding. So if you are doing a measurement down into the ocean, you would do a sounding going down into the ocean. And so then when people started using weather balloons, they said, well, it's like throwing a thermometer up into the air and it goes up. So they called it a sonde. And that was a balloon sonde. And then in the old days, they used to just physically they put a little note on it because when the balloon bursts it could last miles and miles away, so they put a note: if you return this to the Met Office, we'll give you a finder's fee. I don't know the equivalent of what, probably like 50 $100 or something. I don't know. It was something. It was worth doing enough to make it worthwhile. But then in the 30s, they started getting these radio transmitters. So they would be able to use that. So now they're called radio sondes. And what they do is they record temperature, pressure, humidity, wind speed. And there is about 2,000 stations around the world that launch at least one a day and up to four a day, and they can reach up to 30, 35 kilometers. And so we won't get into too much details here, but just to give you the picture, um, when you see a shooting star, it's in the meteor zone. Um, the ozone layer is in the stratosphere, and the what we're used to is the troposphere. And this is defined. Michael will talk about this later, but the troposphere is as you go up in the atmosphere, it gets colder, and that's why when you climb up climb up a mountain, it gets colder as you go up. And so the temperatures get colder with height. But when they first started looking at weather balloons reaching up further, they noticed that the temperature stopped getting colder with height, and they said, oh, that's the tropopause. And then above that, they found that they started getting um, hotter with height. And they call that region the stratosphere. And then it goes through other stuff. But the balloons typically burst around here.
35
So
kilometers. Yeah. Okay.
so now if anybody wants to look at this stuff for themselves, we are mostly using NOAA's IGRA data set. Um, we That's the best for doing large analysis. But like if you're just kind of want to just download a balloon for yourself and look at it and
Yeah, a
uh,
station in your cities. Yeah.
yeah. There is. I just Google University of Wyoming atmospheric soundings, and you can download the weather balloons for yesterday, today, and Michael and I gave us a presentation in 2019 in Tucson, Arizona, at the Doctors for Disaster Preparedness. And so, in preparation for that, these are some slides from there, and we decided to look at Tucson. And so you get this
But
is
before you go on, this was only an example, but we actually analysed over 20 million
yeah,
radio sound
Oh yeah. Oh yeah.
from all over the world for the last 70 years.
yeah,
So
yeah. Mainly since the 50s, the resolution, but there are some that go back to 1909 and 10. But they record pressure, height, temperature, dew point, depression, relative humidity, and humidity. Let's not get too much into the details.
Yeah.
The
Yeah.
key bit
Move.
for this is they record pressure and temperature, and so that's relevant. I got to hand over to Michael soon, but I just to say so. If you've done if you did like chemistry, or yeah, if you did chemistry in high school or in university, you might have heard of the ideal
or
gas law,
physics.
or maybe engineer. A lot of things. If you may have heard of the ideal gas law, and this is a well-known thing called so it says PV equals nRT. So the pressure
Volume
times volume is equal to the number of
or mole of
moles
gas.
times the or, which is 8.314, it's a constant,
I
times the
think that's
temperature.
constant.
And these all have to be in what are called SI units. So instead of Celsius or Fahrenheit, you have to convert the temperature into Kelvin, the pressure in pascals, volume in cubic meters. And what is a mole? A mole is a way of describing the number of molecules in a volume of gas.
Okay.
And it's one
Well,
mole is
specifically, at standard temperature and pressure, it's the number of molecules in 22.4 liters
Mm.
yes, yeah, of a gas.
of
And
a gas.
that works out as this number, which is this big one here.
The great avocado.
Yeah, called this Avogadro's number. It's basically 6 with 23 zeros after it. That's a lot of zeros. Now, the significance of this is that this Michael had this realization when he was looking at the weather balloons that if you actually take this equation, you can, using a bit of basic maths, you can rearrange this. So you can get, if you n divided by v is equal to p divided by RT, and that's significant because r is a constant, and the weather balloon measures at each point. It measures the temperature and the pressure. So that means any point in the atmosphere, if you have the pressure and temperature, you can put this into the formula. You can calculate N divided by V, which is the number of moles of gas per cubic meter. And
Unit volume.
this is the molar density, moles per cubic meter.
This is
E.
truly one of those light bulb moments, even though the formula has been seen centuries.
Yeah,
And
yeah.
Michael came along and then come up with something. You will see the application, which is really the remarkable in terms of changing the paradigm of how we should understand
Yeah. So
chemistry, how it should work.
Maybe
Hold on,
I'll
20
hand
minutes.
this.
I got 20 minutes.
Maybe I'll hand this over
No,
to
I
you.
don't even have 20 minutes.
Yeah.
So
Okay. So
Okay, just summarizing here then what Ronan was saying. What you can see is this is the ideal gas law. Now, I should point out when all the work was being done to determine this law, it was all done on air because it was the only gas at the time. And so air under normal circumstances behaves like an ideal gas because that's how the formula was arrived at using air. But this is the way that it's normally put, and this is the energy form. So basically, what the ideal gas law says is that the work energy, which is PV, which is measured in joules, is equal to the number of moles times a constant times the temperature.
The thermal energy.
Both of these units are in joules, but as with any, so basically, this is called the equation of state of the ideal gas. And an equation of state is an equation that represents all of the variables, the standard variables for, say, a gas. And so you have the pressure, the temperature, and the volume, and the number of moles. But most people are preoccupied with the energy form of it. But by just rearranging this here, just in other words, if you divide the n by v and bring the p over to that side, you get this. It's still the exact same equation of state, but it's put in a different form. But now, when you're looking at moles or at the units are molar density, moles per cubic meter. And uh, a lot of people are preoccupied with the energy representation, but the molar density turns out to be even more interesting.
So,
Um,
by the way, Willie, I know Willie has to leave in a few minutes. So if he does need
I will
to,
read
we
through
keep
this.
going.
Let's
We
move
keep
on. I
going
think
to
you
wrap
can do
this
it,
up.
Michael. Just yeah, because a
But
lot of these let people study the thing. Yeah.
Okay,
yeah,
so this is what's interesting is that if you plot the molar density versus the pressure, you get
so the
these.
ground is at the green bit,
Yes, and this
and
is
then
going up through the atmosphere. So as you go up through the atmosphere, the pressure gets less and less. But molar density behaves in a linear way until you hit the tropopause, and then it changes its behavior.
you want it.
Um,
You want
I
it.
will,
So
I'll go on.
yeah.
So what you're looking at here is this straight line here is what we would expect for the ideal gas. And everybody thought that that would continue like that. Most people still do think that that would continue like that out into space. Uh,
Anybody that thinks on this, rather, sorry to interrupt,
Right.
but
uh,
most people haven't looked at this, or nobody has plotted molar density before
Now,
against.
the thing is, down at this level here, this region is called the boundary layer. This deviation here from the straight line that you would expect is due to water vapor, and water
Yeah.
vapor condenses out, so
Phase
that
change, yeah.
gives a non-ideal level to it. But I just go on a bit
Yeah.
further. So what you look at here is if you find now this is just for one radio sound on this particular day at that particular time. But it holds true for all 20 million radio songs. It's
Oh,
just a position.
universal.
Yes, it's a universal rule. But you can see that this straight line above the tropopause is different than the straight line below the tropopause. It's still behaving like an ideal gas, but a different type of ideal gas. And so can you run? So, okay, let me go back
Yeah,
a second.
yeah,
Let's run this.
So, this point here, where these two straight lines cross, we have identified, and talk about that in a few minutes. We've identified this as a location for the tropopause. And so, what we did was for Tucson, because we were given the talk in Tucson, we took the entire previous year and we plotted where the tropopause occurred for each of the things. So, about every 12 hours, you'll get a new slide. So, Ronan, if you
yeah.
can,
Okay, let me put this on the video here,
yeah,
and then we can start. So on the left hand side here,
It's the
is
regular
the
unit. Yeah.
standard plot that you'd see temperature versus pressure. Sometimes people will plot temperature versus height, but pressure we find is more relevant. And so this is the ground, this is the where the balloon bursts. Each of these gray dots is a measurement that was made by the balloon.
You
That's the
sample the
date.
air as you ascend.
Yeah, I'm explaining this now. This is maybe we'll go through it twice.
I
The
think just
first
run it.
time First time you can look and you can see the way everyone else has been looking at it till now, which is looking at the temperature, and it's kind of all over the place. You can see this bit they call the tropopause because the temperature doesn't decrease with height, with pressure, and then the stratosphere. But then on the right hand side, we look and you see the molar density, and you see it's two straight lines, but they have a different slope, as Michael was saying. So I got to go through this one time, and we'll show just maybe like you can go back and watch it, but look at one panel, and then we'll go back at when it's finished, and you can watch the other panel after Michael's talked about it.
So what you'll notice here is that the tropopause moves up and down on an hourly basis, on a 12-hour basis. And
Hello,
it
Yeah,
can
dynamical
uh,
meteorology.
yeah. So we're up to April to May. So if you're just listening, it's worth viewing this when you get a chance to go back and rewatch this.
Yeah, so you
Um,
can convince yourself that this is a real phenomenon that is uncovered by Michael's new metrics.
and we just did this for Tucson. You can check it for anywhere.
Any station. Yep.
The only difference is if it's a monsoon weather
Right.
or if you're in the poles in an Arctic or Antarctic in the winter. There are differences which we discuss in the
Yeah, those
paper.
are the inversion layer because the boundary layer
Yeah,
goes way up. Yeah.
but pretty much everywhere you can do it. Now, Michael, did you want to just have a comment, maybe just for people to look at when I show this again? I think
Okay, so two things that I point out is that, sorry, I will just
no,
I'll just
like I just describe the thing. Yeah, if you just describe
what
it, I'll
I'm
play it
going
again
to
and then
say
I'll hand
is
it back to you.
uh, if you look down at the bottom, you'll see the line wiggling back and forth, and that's due to water either raining or not raining.
Right.
So that's just something you might be
And then
interested in looking.
also notice, I would say also notice the art, as Michael said, the line that this dashed line, the horizontal line, represents the tropopause, and it moves up and down quite a
Actually,
bit.
quite a bit. Another thing is the magnitude. Look at the weather. Yeah, the serious question about this meteorology is basically what is climate, what is weather, right?
Yeah, so we're just looking at it again, maybe focusing on whichever panel you didn't look at before. And you notice that the two things are plotting the same. These are the same measurements. The only difference here, this is kind of the temperature one is kind of all over the place. Um, that's what people are used to. Whereas here is pretty much two straight lines, plotting in terms of molar density.
Over the
Uh,
few
it
years,
is
yeah. And
more
everywhere is the same.
fundamental
Yep.
it's a more fundamental understanding than plotting in terms of temperature and pressure. And it's based on the ideal gas law. And so I think I
Okay,
would,
let's
when
move
this
on to the
finished,
application after this, yeah.
yeah. So this is basically we published all of that in our working papers, um, and you can still get it. There's a lot more in there and detailed discussion. But since then, we have actually been
Oh,
working
Michael, you
on.
put back your slide.
Yeah, we've been working on. We published some new insights into this. So, Michael, do you want to talk?
Okay,
These
first paper.
papers have been peer reviewed, and this one is in. No, go on to it. Go on.
Okay. So basically, what I'm looking at here is we have things like the Hadley cells, which are a standard uh, sort of model that people have to explain atmospheric circulation. And now, with our new molar density way of analyzing things, we found that we can check this out. So basically, if you know the molar density and if you know the weight of the different molecules in the air, you can calculate the total amount of mass. And we can measure it. One of the things that they do in the weather balloons is they give you the speed and direction with which the air is moving at each spot where they go up through the atmosphere. And so you can calculate the mass flux. Now, the mass flux is the weight of air that's going through a square meter at any time. So it's a vector quantity. If you have the speed and the direction, and this is a bit technical for most people, but you can resolve a vector into east and west components. And so we can measure the total mass flux going towards the poles or towards the
Going
east or
east
west.
west.
Right.
Okay.
So what we did was we took the molar or the mass flux and we started analyzing that for to see what way the atmosphere
Can I
was.
just Michael, just to interrupt, just to say this graph here, what we're showing is how you can use molar density, combine the molar density. So if you know the main change in the atmospheric composition is the water content, and so if you know the water content, which is recorded by the weather balloons, and you know the wind speed, well then you can convert or you can convert the from the water vapor concentration. You can multiply the molar density. You can use that to calculate the specific density, the density of air per cubic meter, and then when
Well, you
you
see,
multiply that by the
density would be
speed,
the actual weighting in kilograms of the
yeah,
air. That's
then you
uh,
can actually multiply that by or scale that by the wind speed,
what
and you can get the mass flux, which is on the bottom right hand corner.
So
You,
what we found, if you this is just for one radio sound, I'll show for a large number in a minute. But what we found is for this particular radio sound that the if you looked at the mass, it's all going into one direction, right? As you go up, and I'll tell you the significance of this in a minute. So
Willie, if you need to leave, you can just log out and we can take.
Yeah, I think you guys are in good hand. Yeah, maybe
Yeah,
I'll
okay.
go
yeah.
about
We're
10:35.
near the end. Okay, okay, that's it.
So basically, the whole business of how the atmosphere circulates and the idea behind the Hadley cells and various things like that arose out of Hadley trying in the hundreds of years ago trying to explain why the trade winds happened and so on, and so the he so
It was
basically the
centuries
different
before they'd invented weather balloons.
Yeah, yeah, yeah.
yes.
Had
So
George
all
Hadley
of
come
these
in the 17th century, by the way.
yeah,
Late.
all of these theories were based on ground measurements. So nobody knew what was happening as you went up through the air, except if you were going up mountains. That's the only time. But
Right.
the idea behind that Hadley circulation was that what happened was the air would flow in the northern hemisphere would flow from north to south. And as it was flowing that way, it heated up. And then when it reached the equator,
You're right.
it was hot enough, it started to rise up. And then Hadley didn't know about the tropopause. And
Yeah.
so about 30 or 40 years before I was born, the tropopause was discovered. And then people realized that the hot air could only get as far as the tropopause because above that the air was too hot for it to rise. And
Do you
so
want
they
to go
said,
on to the next slide and
yeah,
show the
Right,
schematic?
right.
I just show though, but they had it going like this. So you have a circle traveling under the
So on the
tropopause.
graph is north to south, and then on the thing is south to north. Yeah.
So, okay. So this is the standard explanation now for the Hadley cells. So what they say is you have the sunlight here shining down and heating the ground, and the air is moving from north to south, and it's getting hotter as it comes along towards the equator. And then it rises up at the equator, and then it can't go past the tropopause because it's warmer up there. And so it then travels along under the tropopause, and as it's going north, it starts getting cold, and then it falls down, and you get this circulation pattern. And this is what is a Hadley cell. Now, there is another thing called the Brewer-Dobson behavior above the tropopause, but I won't get into that
Yeah,
at the moment.
okay, that's save that for another day because we
So,
can talk.
yes. So basically, what you're looking at is how can we use weather balloon data to check if this is true? So if you launch a weather balloon here and it goes up through the atmosphere and it's measuring the direction of the mass flux, then what you would expect if the Hadley cell was true was that the air, when you're measuring it here, you would get the air traveling in that direction. So down at ground level, it's traveling from north
Maybe
to
just to
south.
put a one short context is that don't you think it's remarkable that this concept is like a cartoon science that's been stuck into everybody's brain and computer climate models, this and that. And
I know,
essentially, no one has checked this.
Yeah.
yes, this
Well, you
is,
couldn't without mass flux. You couldn't
yes.
That's
without
right. That's
mass
the
flux.
unique. That's the power of this molar density concept. That yeah. That's
So,
the consequence. Yes.
so
So, Michael,
Sorry.
basically, what you would say expect is as your balloon was rising up, it would the mass flux will be flowing in this direction, and then somewhere around the middle it would change over and start going north. So you'd expect the behavior to be like this. And so when we started checking with the radiosondes, we found that this wasn't the case at all. That in fact, if you look at these things here, this was where we took 5 years of data from 5 representative climatic regions. So we took an Arctic one, a cool temperate climate, a temperate climate, a subtropical climate, and a tropical climate.
Right.
And we analysed those for 5 years for these typical radiosonde things. But the one thing, for example, I'll go on to the one in Spain. I'll just magnify this up. What
Right.
we found was that instead of the
Oh, Michael, can I just explain to the audience what's been you're plotting here is the mass flux values for the average for what was it for 5 years?
5 years for
Average,
all
or no, this is 5 years plotting it. So
Over time.
it's
Yeah.
showing each value. What we're doing is
it's
smoothing.
been averaged over 31 points, which was
Yeah.
about
So
12.
the monthly average at each point from 2015 to 2020, and at each color represents a different
Different height.
height in the
Cross
atmosphere,
section. Yeah.
And
and so we actually look in the
so
stratosphere.
if you looked at the ground level and then come up, this would be around where the clouds are, and going back. So around here is where the tropopause, the pressure,
And around
uh,
between the two.
the different
Let,
colors. But
the
the
last
one
thing,
thing,
just to explain the graph for the audience.
yeah,
So if the value goes above the line, the positive value, that means that the north south, that the air is heading north, or is heading from the north. Is it? Yeah, it's heading to the north. If it goes above the line, and if it goes below, it's going to the south. And the thing is that all of the heights, they're all going in tandem. In
they're
That
all
is
Spain,
going
going up and
in.
down together at all heights.
north and
But
south together.
what it says now is instead of the atmosphere going around continuously in this Hadley circulation, the whole the convective model, as it were, the whole atmosphere is acting like a giant pendulum. So it travels in from north to south, and then after a couple of days, it comes and starts going in the opposite direction. So you can see it rocking back and forth. So what this is saying is here it's going from north to south, then it comes back down again, up again, down again. So this is saying that the whole atmosphere is moving back and forward, and it's not a
together.
circulation pattern. So this
So
this
move
just
on to the next. We've just wrapped things up.
so if
Yeah.
we take the average over the entire
5 minutes.
period, you can see that we don't get the back and forth or the Hadley cell
The sign
behavior.
switching, yeah, the sign switching
Yeah.
of the flow of the mass flux.
What you're seeing is that the whole atmosphere, the mass flux, is going on average over the whole 5 years in this
Same
direction.
direction.
This one is in a subtropical one, and this one is in a tropical region. Now you can see you do get a change as you go up. It changes from zero and goes in the other direction.
Mauritania, just for Mauritania.
The tropical thing, but and you say, right, well, that's the Hadley cell circulation model. But the problem is that it's going in the opposite direction. This is the way it should be going for the Hadley cell thing. So even though this is the only one where we found a change in the mid-troposphere, it wasn't. It was going in the wrong direction. And the other thing was that the mass flux on average at the ground level wasn't equal to the total mass flux going in the other direction.
Well, I think that's kind of just give an overview. We go into a lot more detail in the actual paper, and that was
Yeah.
actually just a preliminary one because we analysed 5 stations. No, before we did the paper, we've analysed hundreds and hundreds all
But
around.
what this new way of analysing the atmosphere does is it tells us that the balloon data doesn't support the various circulation cell models like the Hadley cell and that.
And nobody had done that before because before they were just measuring the wind speed and they weren't measuring the mass flux. So people were just
Right, and
speculating.
notice that you cannot use satellite retrieval to do this. You need to measure the thing in situ, right there. That's where the balloon data comes in. Very unique, very special, and the only way that can allow a bit of a resolution of this mass flow, which is
And
very powerful. No
this,
computer model.
yeah, this paper has gone through the standard peer review process.
Yes,
So
yes.
it's,
So just do you want to talk briefly about our most recent papers?
Yeah, next graph, please.
Yeah.
okay, we'll go on to this. Okay, so what we looked at is we again used the weather balloon data to look at the tropopause, that line that we had moving up and down. And what we found was that the quality of data now has improved tremendously. But we found this set of data which took a reading every second as you go up through the atmosphere. They were called ozone sondes, but they measured, besides measuring water vapor and temperature and pressure, they also measured the ozone concentration. And also they had a very accurate reading of the water vapor content all the way up to where the balloon
Hey,
was.
so just for this thing for the audience, in the paper we look at all 4. We look at and the standard WMO definition of the tropopause. We look at the ozone based and also the water vapor. But here I think Michael is just got to point out how
So
the molar density is a very useful tool for calculating the tropopause.
So this is a very high resolution data set for these for a whole year in Valencia. They took very close readings, but it's just to illustrate. This is as you normally see the temperature plotted with altitude, and
All right,
what you can
I go now. Thank you, guys.
Okay, thanks, Willie.
I just leave it there, and then whatever, kick me out, kick me out.
Yes, yeah.
At least
I don't know. You can turn the just.
my rich
Oh yeah.
appointment
Okay.
can be, my very nice.
Your nice
my
apartment.
beautiful, expensive appointment.
His AI generated apartment. Okay, thanks, Willie.
So what we're looking at here is the standard way the temperature is plotted with altitude. And what we're saying is you can also, instead of plotting the temperature versus altitude, you can plot it versus pressure. This is more useful in that it tells you the amount of air. As you can see from this, about 60% of the air is in the tropopause. But if we go on just taking, that's your normal one that you see,
Temperature
and
versus altitude or height.
and this is what's called the lapse rate. So if you look at the temperature versus thing, from taking measurements on mountains and that, for hundreds of years, people have known that as you go up through at different altitudes, the temperature drops off at about nearly 7 degrees per kilometer, or nearly 8 degrees per mile in Fahrenheit. And this is how, if you were to plot that with pressure, you'd see that you get a curve, a different curve for this straight line. Up until the discovery of the tropopause, people thought that this was going to go on forever like that. Um,
Onto space.
onto space. Now, what we're saying is you see the behavior with respect to temperature, but now if we look and plot instead the molar density versus the pressure, you can see with this high quality data set, you can see two clear straight lines. And again, you can see if you fit the bottom one with this, you get a very high correlation for the straight line. It's point r squared 0.999. Basically, if the r squared has a value of 1, it means that it's an absolute straight line. And so you can see this
Or
is
an
near.
absolute perfect fit to the data. It fits
Yeah,
the data exactly.
yeah.
The data is a perfect thing,
So
but
this is showing if you plot the molar density versus pressure, you could see you would get this exponential decay because the pressure drops off exponentially
I,
with altitude.
I just for people that are unfamiliar with this thing. So, the pressure falls off exponentially with height. So when you plot you get a straight line in against pressure. When you plot that in terms of against height, it ends up with these curves, but exponential curves. But what Michael is showing there is that the shape of the curve changes above the tropopause.
The reason I'm all just showing this is that this shows that the two forms of representing the ideal gas law work, but in a slightly different way. What we have found was that looking at these high quality ozone sondes and that sort of thing, we found that the tropopause, you could use four different variables: the temperature, the water vapor, the ozone concentration, and uh, molar
The
density.
water vapor
Yeah,
and the molar density.
yes.
So
And
okay,
they all give you the
the
exact same.
same result. But the molar density gives the cleanest. Is the simplest. So that's what, in our opinion. So okay, so I think really what we wanted to just kind of give people an overview. We obviously there's a it, just there's a lot of technical stuff there, but also just to let you know what we're doing and why we think this is.
Yeah, what we're just doing in this first bit is just taking two of our dozens of papers that we put out there, and we've just looked at it, shallow look at it, but just showing how revolutionary this new approach to analyzing terms in terms of molar density and that is advancing the whole science. And it's also allowing us to check out a lot of the assumptions that had been made that nobody bothered to check. And what we find is that a lot of the assumptions are just
So we have other papers following on from that, but it's taken a long time to get these published in the peer reviewed journals. Our A lot of what we had to say was in those OPRJ papers. The peer review process is a lot lower, it's longer. It can take years to get a paper published in the peer review, especially if it's
actually,
going against existing paradigms, which is what this stuff is doing. But we
uh,
have those papers, and that was published in May last year. That last one, And then we have other ones that we're doing, and we can talk about
Yeah,
them on the podcast
this is
when they're.
only a small fraction of the weather balloon data that we've looked at. And
Yeah,
we have been using the weather balloon data just to check the assumptions in the models, because these assumptions had never been checked. And what we're finding is that using these new approaches to looking at the weather balloon data, which are not new in the sense that it's old analysis, but it's applying these analyses to weather balloon data, that's what's new.
yeah.
Uh, and then that is finding that the models, assumptions in the models are not correct. They're not
So
supported by data.
okay, so if you're still listening with us to the end, thank you for staying to the end, and uh, like and subscribe and share the video and all of that stuff. And let's wrap it up. Leave it at that for today. What do you think,
Okay?
Michael? Yeah.
Yeah, that's fine with me.
Okay.
Bye.